Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Physical Sciences students. Now we are dealing with the paper on applied electronics, and in this paper, which is intended for the 4th semester, in the unit 2 we have got positive ray analysis, Bain bridge, mass spectrograph, isotopes and so on. And when I talk to you about isotopes, I should tell you, in continuation with the lecture I delivered at the last occasion, we were discussing about the positive rays and what are the constituents of positive rays. And you all know that J.J. Thomson is the discoverer of the electron. In the contents which I will be dealing with in this lecture too, not only the specific charge E by m, E by m is called the specific charge of the electron. Not only the electron, he will be determining, or he determined the E by m values for the constituents of positive rays. And again, if the discharge tube is filled up with certain other gases, he was able to find the E by m values varying with different values. This made people to think of mass numbers, isotopes, a better knowledge on nuclear physics. And this discovery of isotopes, the whole thing, whatever I am now talking about, the discovery of the electron, the mass spectrographs, isotopes and so on, this went from the domain of physics to chemistry and the biologists and the medical people. You all know about cobalt therapy, the isotopes of very many isotopes which are used for curing cancer patients. And so this important discovery which was made by Thomson on positive rays. So the contents or Thomson's experiment on positive rays, contents of positive rays, and identifying isotopes. In the Thomson's experiment, he wanted to know if all the positive charge was carried by particles of the same type, a positive equivalent of the electron. He wanted to investigate that. He used a method which would show whether there were different types of carriers for the positive charge. At that time, many things remained unknown. He sent a narrow beam of positive rays between 2 brass plates and applied an electric field that bent the beam of the charged particles in the x prime direction. Then he went on to apply the magnetic field also, before going further, I should tell you what are positive rays. In continuation with what I have been telling you in the last time, what are positive rays? You know the discovery of electrons. What are electrons? Electrons are nothing but the constituents of cathode rays, the rays going from the cathode. On the other hand, it was found by Goldstein that rays are going towards in the opposite direction. That is, apart from the cathode rays, there are rays going in the opposite direction. They are called the positive rays, or they were called the canal rays or channel rays. The word channel came because the cathode was perforated. They used they drilled holes in the cathode. The perforated cathodes, the particles are going in the opposite direction. That are the cathode rays. You know, cathode rays are made up of electrons. The electrons are discovered by J.J. Thomson. In addition to the discovery of electrons, they found that, you know, cathode rays are made up of electrons, negatively charged particles. Then you have what are called positive rays, which are moving in the opposite direction compared to that of the cathode rays. And it is the aim of the talk to investigate the constituents of the positive rays. What are the constituents of positive rays? And not only so, to investigate this, you apply electric field and magnetic field. And not only about the positive rays, you have other gases in the discharge tube. You fill up the gas discharge tube with helium and then neon. You find new discoveries. That is a very important thing. You come across the concept of mass numbers. You go inside the nucleus. Electrons are peripheral particles surrounding, revolving around an atom. Electrons are revolving around the nucleus. You have the positive rays, means you are going inside the nucleus. What are positive rays? They are nothing but the ions of hydrogen atoms. Okay. Now, these things ought to be investigated. We have to find the E by M values of the electrons as well as that of the constituents of the positive rays. Okay. So, you subject these positive rays to an electric field, and not only to an electric field and also to a magnetic field. You have the discharge tube. I told you in the last lecture, lot of work was done. Volumes have been written by J.J. Thomson on the title Discharge of Electricity Through Gases. So, you have a rarefied gas in a discharge tube. That means you take a discharge tube, take a Crookes tube, you take a glass tube, have a cathode and anode, apply a large positive potential, and see, when you apply a potential, how does what happens inside the tube? That is the investigation. Now, you have a rarefied gas. You reduce the amount of air contained in the glass tube. You reduce the pressure. When you go down to very low pressures, what you observe in the discharge tube is the thing about which lot of investigations are made by J.J. Thomson as well as many others following Thomson, his students, his collaborators, and many others did works on. That led to the idea of mass numbers, isotopes, and so on. This is a diagram of the discharge tube used to produce positive rays in J.J. Thomson's investigation. The tube consists of a spherical glass bottle containing a gas at low pressure with electrodes at each end of the tube. He then put coils at the same point, generating a magnetic field. As I told you just now, he subjects these particles to both fields, electric field as well as a magnetic field, to bend the beam along the YY prime direction. The particles are subjected to two mutually perpendicular fields. One is the electric field, the other is the magnetic field, and you have here the anode and you have got a cathode here. Some of the gas in the tube will be ionized by heat or by the application of X-rays. Ionization liberates what? Electrons. Ionization, liberation of electrons, which rush away from the negatively charged cathode. The positively charged nuclei rush towards the cathode. The positively charged nucleus. What is the positively charged nucleus of the hydrogen atom? When you ionize the hydrogen atom, you got a hydrogen gas in a discharge tube. By ionizing hydrogen gas, what do you get? You remove the electron. You end up with a proton. So, the protons will rush towards the cathode, right? Because the cathode is negatively charged. So, the positive ion of the hydrogen atom is nothing but it is the constituent of the so-called the positive rays. What the positive rays contain positively charged particles. Cathode rays contain electrons which are negatively charged. On the other hand, positive rays are nothing but the positively charged protons, right? At that time, protons remain unknown, right? The hydrogen atom, you discover the electron, and what remains inside the nucleus, right? Now, your proton is inside in the hydrogen atom, you got a proton and electron. So, strip the electron, ionize the hydrogen atom, what remains is the proton. Proton will obviously move towards the cathode of the discharge tube. So, now we want to investigate what happens to these cathode rays when you apply both fields in a very detailed manner. In Thomson's apparatus, the cathode ray was a fine tube. Some of the positive ions would emerge from the other side of the cathode. The positive rays were originally called Canals-Strahlen. Canal means, as I told you, channel rays, because the cathode was perforated. It had holes, so they are called channel rays or canal rays, because they emerge from these slits in the cathode or the perforations in the cathode. Okay, so you now pass on to fact that Thomson's apparatus deflected the positive rays using an electric field in the x prime direction and a magnetic field in the y prime direction before allowing them to fall on the photographic plate. The action of both fields makes ions of the same mass to charge ratio m by e, the mass to charge ratio, to fall on the same parabolic curves, which I will show in detail in the time to come. Fast ions are deflected less than slower ions, but this only affects their positions of the curve, not which curve they fall on. If the gas in the discharge tube contains different sorts of ions with different specific masses, they will be split into separate parabola by the time they hit the photographic plate. And you have here the deflection suffered by the charged particle of charge q. You see the q is the charge carried by the particle. It may be an electron or it may be the proton. Positive rays are made up of protons, and so positively charged particles are deflected along a parabolic path as they pass through the electric field. What will be the magnitude of the deflection? You have to take into account the length of the plate, how long does the particle stay between the plates, or how long does it experience the electric field. So, parallel to the plate, when the particle is moving, the positively charged particle enters the electric field with velocity Vz. Vz velocity will be length divided by time. L is the length of the field and T the time for the particle to stay in the field. So, Vz is the same as when the particles leave the field perpendicular to the plate of the electric field x prime. This forces the electron to move in the, let me read once again. Thomson put a photographic plate at the end of the apparatus to record the different parabola. He found that the gases he was investigating contained ions with many different values of q by m, charge to mass ratio, and measured the parabola to find these values. We will have a short break at this point. Welcome back to the break. I showed the animation in which you saw the deflection experienced by the charged particle when it is subjected to an electric field. Similarly, this animation shows the deflection suffered by the charged particle because of the magnetic field. So, positively charged particles are deflected around the arc of a circle as they pass through the magnetic field. So, you write in standard textbooks HEV or BQB, B the strength of the magnetic field, Q is the charge and V is the velocity. Then you have to apply the Fleming's left hand thumb rule if you are subjecting a particle to electric field and magnetic field, you know, the left hand thumb rule, to find the resultant direction in which the particle will be moving. So, whenever you got a charged particle and the application of both fields, electric field and the magnetic field, you have to bring back the Fleming's left hand thumb rule. You can now tell me in which direction the particle will move, the charged particle will move. You know, thumb indicates the direction in which the particle will be moving. The other two fingers, they show the directions of the electric and magnetic fields. So, the magnitude of their velocity is unchanged by the magnetic field. The particles retain their initial speed. The acceleration only causes their direction to change. Acceleration in the magnetic field, the YZ plane, the force experienced is ma, that is equal to mv square by r, that is equal to bqv. What is b? B is the strength of the magnetic field, q is the charge of the particle, and v is the velocity of the particle. Whatever equation that I am showing now is applicable to the electron as well as the proton, which constitutes the positive rays. Since the speed of is not changing, the magnitude of V is V naught. Rearranging the above equation, it gives the radius of curvature R is equal to mvz by bq. Deflection due to the magnetic field is given by an expression phi will be equal to LA into QB by m into V naught. This is what you get now. You understand kind of deflection that will be suffered by a charged particle because the electric field as well as because the magnetic field, as the animations show. Now, we have both fields simultaneously, and if the particle obviously experiences the cross fields, the influence of the two fields, you can write the electric field reflects the charged particle through an angle theta in the x prime plane. Tan theta will be QE by m into L by Vz square. This causes a horizontal deflection in the x direction. So, deflection cost will be x is equal to CL, the constant that depends upon the kind of apparatus, the size and shape of the apparatus. Q is the charge multiplied by the strength of the electric field. M is the mass of the particle. V is its velocity. The magnetic field reflects the charged particle through an angle phi. That will be, angle phi will be given by LA into QB by MVZ. This causes a vertical reflection in the y direction, something like x, you have y here. C2 is again another constant that depends upon the shape and size of the field or the, the apparatus. QB by MVZ. Putting these two together, you have y square by x is equal to C2 square by C1, Q square B square divided by M square VZ square divided by QE divided by MVX square. That turns out to be C3, again a constant, Q by M into B square by E. This is the equation to a parabola, right? The field strengths are constant. All the particles with the same ratio of charge to mass will fall on the same particle, on the same parabola. This is a very important sentence. If the m by E value or E by m, we call it E by m, charge to mass ratio or mass to charge ratio, if the E by m value is the same for all the particles, then the parabola which will be hitting, the particle will be hitting on the screen, on the phosphorus screen, that will be, you have the parabola m equal to q by m equal to 1, 2 and 4. What is that? The charge divided by mass, right? Okay. And charge divided by mass. Now, what is the mass of the hydrogen nucleus? What is the mass of the helium nucleus? Helium contains what? You got 2 protons and 2 neutrons, and you got neon. Neon contains 10 protons, okay, 10 protons, 10 neutrons. In some cases, there will be, the value will be 22 and so on. So, depending upon the mass of the nuclei, mass of the particle, anyway you strip and then you are talking about a positively charged particle. If you ionize the hydrogen atom, you are ending up with a proton. Q by m, you know, the value of Q by m will be different for the ion of hydrogen atom or the ion of hydrogen molecule or the ion of helium atom. So, depending upon the m value, the mass is changing, the charge also will be changing, because the number of protons in the nucleus will be changing. Depending upon that, you can differentiate between the proton and the helium nucleus and neon nucleus and so on. Okay. This is what I showed you just now. Try changing them electric field strength, magnetic field strength and the energy of the or the velocity of the ions or the energy of the ray using sliders below. See how the change and shape of the position of the parabola. Anyway, okay, you have got the photograph, you have the positive ray entering into electric field and magnetic field. Then if both fields are applied, then the photographic plate is here on which the particle will be hitting. You have a particle deflected in this direction. I showed the animation. Now I am showing the static pictures and repeating the same thing. Deflection caused on the charged particle, positive charged particle by the electric field. Secondly, the deflection caused by the electric field and then the magnetic field. Okay. Then the angle through which the positively charged particle is reflected goes to a value of this kind. Then both fields if you are applying, then you have a parabolic thing. These things we saw earlier. So, now at first Thomson, when he was doing this kind of experiments, he could produce only a single line on the photographs. The single line is due to what? Is due to, you know, hydrogen is something which is present everywhere. Water vapor, you got H2O, because of the presence of hydrogen, you will be having always streak or a parabola which is caused by the presence of the ion of hydrogen atom. The ion of hydrogen atom is nothing but a proton. So, from its position, Thomson calculated if it was the hydrogen ion that, what is hydrogen ion? It is nothing but a proton, right? What are positive rays? Positive rays or positive ions. Positive rays are made up of positive ions. For a hydrogen atom, the positive ion is you strip the electron, you end up with a proton. So, hydrogen ion is nothing but a proton that Wien had found, as its mass to charge ratio was 2000 times greater than the electron. You know now the mass of the proton. Now, at that time, the protons remained unknown. Anyway, you have to assume that you are living in the world when Thomson lived, or Bainbridge or Aston and those people lived, or Millikan. We don't know, we are not having any knowledge. So, from these lectures, we make you to understand the historical developments which took place along with the discovery of the electron discovery of positive rays and so on. So, even if the discharge tube contained other gases, only this hydrogen line was produced. What does it mean? Even if the discharge tube contained other gases, only this hydrogen atom line was produced. Produced means, as I told you just now, hydrogen will be always present. It looked like ions of hydrogen were carrying positive charge in the same way that electrons carried negative charge. You know, electrons carry negative charge. Similarly, the ions of hydrogen should be carrying positive charge. Now, all of you know, but at that time, Thomson was thinking that he was not knowing about protons and so on. So, Thomson wants to make it very sure by using a very large discharge tube, and at very low pressure, he managed to produce a second line with twice the specific charge of the hydrogen ion. How does the specific charge E by M or M by E, it becomes twice. What is that? M by E. M by E becomes twice means what? There should be 2 protons, right? There will be 2 protons. Thomson identified this ion as an ionized hydrogen molecule. It is very interesting. Hydrogen molecule contains what? 2 hydrogen atoms, right? Hydrogen molecule is made up of 2 hydrogen atoms. So, obviously, the mass becomes, mass of the central portion. You forget about the electron. The mass of the electron is very, very small. It is 2000 times less as that of the mass of the proton. Therefore, that is not the important thing. The mass of the nucleus becomes 2 times. That means, instead of hydrogen atom, you got a hydrogen molecule. Thomson identified this ion as an ionized hydrogen molecule. 2 atoms of hydrogen bond together to form a molecule. So, we observe from Thomson's experiment, number 1, the positive rays are nothing but the ions of hydrogen atoms. If the charge to mass ratio or the mass becomes double, that means you are talking about the ion of the hydrogen molecule. So, if the mass becomes 2, as I told you, the hydrogen molecule comes into the picture. Similarly, if the mass becomes 4 times, you go to, when do you get the mass M by E to become 4 times the mass of the proton? That means you are talking about what kind of atom? It is helium atom, because helium contains 2 hydrogen and 2 protons and 2 neutrons. Let me now summarize as to what I spoke to you so far. Thomson's experiments on positive rays undoubtedly showed that positive rays are nothing but ions of hydrogen atoms. What is ion of hydrogen atom? Is the proton. Thomson applied both electric and magnetic fields to determine the E by M values of positive rays. When the tube contained other gases like helium, etc., the isotopes of these atoms were found. Let us now pass on to the question session. The questions are: what are positive rays? How did Thomson determine the E by M values of the constituents of positive rays? What happens to E by M values if the discharge tube is filled with helium and neon? What are mass numbers? With this, we come to the end of this lecture, and we will see in detail about what I told you just now. If the discharge tube contains other gases, what happens to the mass by charge ratio and so on. With this, we come to the end of this lecture. Thank you.